In this chapter, we're going to be looking at the next functional group, which is carboxylic acids and their derivatives. So really, we're going to be looking at carboxylic acids, esters, and amides. So carboxylic acid has a carbonyl group with an OH attached to it, so a hydroxyl attached to it. And then the R group, on the carbon. So this right here is called the carboxyl group. So carboxyl group. Okay. And then the esters have a carbonyl group as well, but then an OR group bonded to it. So the R could be, anything. But the O bonded to the carbonyl group, that's what makes it the ester. With the R as well. Okay. And then amides have the carbonyl group and then an N bonded to the carbon in the carbonyl group. And then the N can have either two hydrogen attached to it, or a hydrogen in an R group, or no hydrogen and just two R groups. So we'll look at the difference there. So kind of, thinking back to amines. So this isn't an amine, it's an amide, but it has, if it's not hydrogen, then that's the substituted, the groups that are substituted for the hydrogen. So esters and amides are derived from carboxylic acids, and we'll look at those reactions later on in the chapter, but for now we're just going to talk about the properties and how to name each of these. So carboxylic acids and esters and amides, they all contain a carbonyl group, and they're either bonded to an oxygen or nitrogen. And because of this, they're all polar, which makes them have higher boiling points than just alkanes that have similar molecular weights. So they have high boiling points because of that, because of their polarity. Okay, so esters are not able to hydrogen bond with itself because they don't have the hydrogen attached to oxygen or nitrogen. So here's our ester, right? There's not a hydrogen attached to that oxygen. So that's why it's unable to hydrogen bond with itself. Now it still can hydrogen bond with water, just not itself. So carboxylic acids, they have a hydrogen attached to the oxygen, and then amides have a hydrogen attached to the nitrogen. So they are able to hydrogen bond among themselves. And amides, so only if there's a hydrogen on the nitrogen can that happen. So if we have N with two R groups, then that wouldn't be able to take place. Okay. And we'll talk about phosphoric acid esters later in the chapter. Because carboxylic acids, esters, and amides all have an electronegative atom attached to the carbon in the carbonyl group, they're able to undergo carbonyl group substitution reactions. So this is how the derivatives are actually produced from the carboxylic acids, and we'll get further, we'll go further into that later in the chapter, kind of see what that looks like. But the portion that remains unchanged in the substitution reaction is called the acyl group, and it's in this box. So this box right here is, nothing happens to that during the reaction. Right here. So what happens is the OH is removed and either the OR group comes in to form the ester, or the NH, or whatever one of these ends come in to form the amide. So we'll look closer at these reactions later, but it's just called the carbonyl group substitution reaction. And again, we can do that because of the oxygen being bonded to the carbonyl group. Okay, carboxylic acids are similar to weak acids, and they're able to transfer a hydrogen to a base. And when they do that, it establishes an equilibrium. So it's a neutralization reaction between an acid and a base. So carboxylic acids are able to form hydrogen bonds with each other, which we've already kind of mentioned. And so it gives them high boiling points. It's even higher than alcohols. So far, when we've looked at boiling points, alcohols have been the highest. But carboxylic acids actually have higher boiling points than alcohols do, that with, as long as they have similar molecular weights. And then smaller carboxylic acids are soluble in water, and that's the same trend that we've seen throughout the functional groups. As long as it's if they have small carbon chains, they're able to dissolve in water. If they don't, then they're insoluble. And then small carboxylic acids are also volatile, so that just means they easily evaporate, and they have strong odors. So hopefully you'll see that in lab this week or next week. And then larger carboxylic acids are odorless solids. Okay, so you should be able to see that in the lab this week. And then in our picture here, it just shows hydrogen bonding between the carboxylic acids. Okay, so right here, we have one, and then over here the other, and then where the red dots are, that's where the hydrogen bonding is taking place. So that has strong intermolecular forces there, which makes it have that higher boiling point. Okay, so to name carboxylic acids, we replace the E of the corresponding alkane with OIC acid, so oic acid. So we number the chain of the carbon chain, beginning with the carbon in the carbonyl group. So here's some examples. So here we have 1, 2, 3 carbons, so that we know that's propane. Okay, so propane. But then to name the carboxylic acid, we just remove the E and then put OIC and then acid. Propanoic acid. So kind of like aldehydes, we don't need to number where the carboxyl group is. It's always on number 1, okay? And then on the next one, we have 3-methyl butanoic acid. So again, we're numbering starting with the carbon in the carbonyl group, and then numbering over this way, okay? So we need to name our substituents, and then we can name the carboxylic acid. Okay, this last one, so the first name listed is the common name, and a lot of the smaller carboxylic acids are named using common names, but we also have the IUPAC name underneath. So we have 3 carbons, which is propane. So propane, and then we change the E to OIC, so propanoic acid. And then they name the OH, the hydroxyl group, so 2-hydroxypropanoic acid. So within the IUPAC system, when there's more than one functional group present, you have to follow the priority of the functional groups. So carboxylic acid has the highest priority. So just to see here, so carboxylic acid has the highest priority, and then down here alkanes has the lowest priority. Okay, so if you have an aldehyde and a carboxylic acid in the same molecule, we would name it as a carboxylic acid and then name the aldehyde as a functional group. Kind of like what we saw with the amines. If we had an aldehyde and an amine in the aldehyde, then we would name the amine as a functional group instead of as an amine. So you have to follow the priority there. Okay, so the common names of carboxylic acid are used, and this is the list of them from your book in table 1. So we have just the simple ones here on the right. Okay, I'm going to kind of show you these here in just a minute. And then we have some unsaturated and aromatic acids over here that we'll be using. Okay, and then the dicarboxylic acids, which I'm going to talk about here in just a second. So these are just the common names of those instead of the IUPAC. Okay, so to name common names for the carboxylic acids, the prefix form, I'm going to write this down for you. So form, acid, propion, and butyrate. So these prefixes are used in the common names. So if it's form, it only has 1 carbon. Okay, acid has 2, propion has 3, and butyrate has 4. So I'm going to give you some examples of that in a second. And then to label the substituents in the carbon chain, we use Greek letters for the adjacent carbons. So alpha is the carbon next to the carboxylic acid, the functional group, then beta, then gamma, okay, and so on. So those are just used to label substituents. Okay, so let me give you some examples here real quick. Okay, so here we have 1 carbon. Oops. Okay, and this is a carboxylic acid. So since we have 1 carbon, we're going to use form and then put ic on the end and then acid. So that would be the common name for this carboxylic acid. Now for the IUPAC name, we would just use methane, right? Because there's only 1 carbon. Drop the N, or I'm sorry, drop the E. Methanoic acid would be the IUPAC name. Okay, and then for 2 carbons, we have the prefix acid or acete, I don't know. Okay, and then we would put ic on the end, acetic acid. But if it was the IUPAC name, then we would just name it with 2 carbons, so it's ethane, ethanoic acid. Okay, same thing. And then 3 carbons. Okay, so 3 carbons would be propion, and then we put, whoops, let's try that again. And then we put ic on the end and acid. But the IUPAC name, it would be propane. But then we add OIC, propanoic acid. Okay. And then for 4 carbons, so we have CH3, CH2, CH2, CO, whoops. Got too high. Okay, for 4 carbons, it would be butyrate. And then add the N, so butyric acid. Or it's butane, take the E off, butanoic acid. And so you can kind of see there how the common names relate to the IUPAC names. And then if we wanted to throw in a substituent, you know, let's say we have CH3, CH with a methyl group here, CH2, COOH. Okay, Okay, so we could still say butyric, but then we have to add in our methyl group. So it'd be beta. That's right, that's on the beta carbon. So beta methyl butyric acid. So a little bit different, but that I wanted to go through that with you just because the common names are used quite a bit. Okay. So when the carboxylic acid loses the hydroxyl group, the OH group, we name it by replacing ic with OYL. Okay. So instead of down here we have, this would have been propanoic acid, you know, if we had the OH there, but when that OH gets removed, we take ic off and add OYL, so propanoyl group. Okay, so it becomes a group instead of the acid. Same thing over here, so instead of benzoic acid, it's benzoyl group. The only exception to that is acetyl or acetic acid. When the OH comes off, it's acetyl group instead of acetyl group. So there is one exception to that. Okay, and then if you have two carboxyl groups in your carboxylic acid, then we remove we say the name of the alkane, and then we put DIOIC acid. So kind of like what we've done previously with functional groups, is we go ahead and say the name of the alkane, and then put oic di. For aldehydes, it was all diol. For ketones, it was one, so dione. So it's very similar to how we've named those in the past. So again, simple carboxylic acids are named by their common names, but we have the IUPAC names underneath there. So since there's two carbons, then we would say ethane dioic acid. Okay, this one has 4 carbons, so butane dioic acid, and then 5 carbons, pentane dioic acid. And we know that the carboxyl groups are on the end, so there's no need to label where they are. Okay, let's go through these examples here. Okay, so I'm going to start by numbering our carbon chain. So again, we're going to start numbering at the carbon in the carbonyl group. So 1, 2, 3, 4, 5. Okay, so we want the longest carbon chain, so that's going to be pentane. Whoops, pressed the wrong thing. Okay, so it's pentane. So I'm going to go ahead and write pentane. Okay, so since it's a carboxylic acid, I can remove the E and put pentanoic acid. Okay, but we're not done because we do have some substituents, right? So we have this right here. So that is 3 carbons, so we know that's propyl, but because it's attached in the middle carbon there, it's going to be isopropyl. So that was our second carbon, so 1, 2. So isopropyl is on the second carbon, so we can name it 2-isopropyl pentanoic acid. Okay, so that was number 1. Number 2, go back here. Okay, so we're going to start numbering 1, 2, 3, 4. Okay, so on the third carbon we have a bromine. So we're going to say 3-bromo. Okay, and there were 4 carbons in our carbon chain, so that's butane. And we're going to take the E off and add OIC and acid. So 3-bromobutanoic acid. Okay, number 3. so again, let's number. We have 1, 2, 3, 4. Okay, so we have a couple things here. We have a double bond, and we have an OH group, and our carboxyl group, okay? So we're gonna start by naming the OH group, which is on carbon 4. So we're gonna say 4-hydroxy, and then we can number where the double bond is. Whoops. Okay, the double bond is on the second carbon. So we're gonna put 2. And then our carbon chain was 4 carbons long, so it's butane. Okay, but since we have that double bond, we have to change the A to E. Okay, that tells us we have that double bond. And then drop the other E, so it's not just butene. So we drop the E and put OIC, butanoic acid. Okay. Okay, and then over here, we have the carboxyl group attached to a benzene ring, and then we have 2 methyl groups. So this is going to be carbon 1. Let me change colors here. So this is going to be carbon 1, 2, 3, 4, 5. Okay, so we don't have to label where the carboxylic acid group is because it's always going to be a 1. So we do need to label where our methyl groups are on 2 and 5. So we'll start with that. Okay, so number 4, we have 2, 5, and that's dimethyl. Okay, and then it's a benzene ring. That's our parent chain. So we're gonna name it benz, and we're gonna drop the ending there and add OIC, so we get benzoic acid. Okay, and then number 5, we have 1, 2, 3. Okay, so we have an amine group here, amino group. So remember, it has lower priority than the carboxylic acid, so we're going to name it as a carboxylic acid. Okay, so we'll start by naming the amino group, which is on 3. So it'll be 3 amino, and then we had 3 carbons in our parent chain, so it's propane. So we drop the E and put OIC acid, so 3-amino propanoic acid. Okay, and then the last one, we have another benzene ring, but we have 3 carbons here, so that's propyl, but since it's attached to the middle one, it's isopropyl, and then we have our carboxyl group here. So that's going to be on carbon 1, 2, 3, 4. So we're going to name isopropyl first. Whoops. So it's going to be 4 or P, either one. 4 isopropyl. And then the benzene ring, and replace the ending with OIC acid. So 4 isopropyl benzoic acid. Okay, so now we're going to draw these carboxylic acids. So the first one we have is 2-methyl propanoic acid. So our parent chain is going to be propane. So we have propane with the carboxyl group on the end. So there's our carboxyl group, and the carbon from that is our first carbon. So then we'll have on our second carbon we have the methyl group, and then we have one more. Okay, because again our parent chain is made up of 3 carbons. Okay, and that is it for that. Okay, on the next one we have hexane for our parent chain. So we're going to have again the carboxyl group right there, and then we'll have 6 carbons attached there, but we've got all these methyl groups. So we have 2 on the second carbon, which is going to be this one. So we're going to have a methyl group here, methyl group here. Okay, and then we have carbon 3, carbon 4, and then carbon 5 has a methyl group. And then our last carbon on the end. So 1, 2, 3, 4, 5, 6. And you can do the line structures as well. I'm just for some reason doing condensed formulas. Okay, then on number 3, we have 2,4,6 trinitrobenzoic acid. So benzoic means we have a benzene ring. Okay, here's our benzene ring. And then the carboxyl group is going to be on carbon 1 in the benzene ring. And then it says we have 3 nitro groups, so 1 on 2. So since this carbon here is number 1, so this one is going to be 2. We're going to have a nitro group, which is NO2, and then 1 on 4, so 3 and then 4. And then 1 on 6. Uh-oh, I ran out of room. Put it like that. Okay, so that was number 3. Okay, the number 4 is hexane dioic acid. So we're going to draw hexane, 1, 2, 3, 4, 5, 6. Okay, and then it says dioic, so we know we have 2 carboxyl groups. So I'm going to put one here. And I'm going to put one here. So remember, they go on the end, so we don't need to label them. We just know that they're on the end. Okay. Number 5, we have 4-hydroxyheptanoic acid. So I'm going to start with our parent chain. It's heptane, so that's 7. 1, 2, 3, 4, 5, 6, 7. Okay. So on the first one, we're going to put our carboxyl group. And then it says on number 4, we have a OH group. 1, 2, 3, 4. And that's it. And then last one is number 6, is 2-butanoic acid. Okay, so we have 1, 2, 3, 4, so butane. But it says we have a double bond, but let's go ahead and put our carboxyl group in right there. So that's carbon 1. Carbon 2 has a double bond, so we can put that, and we're done.